Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Berthold Stöger.
Professor,
Don't worry, you will be. We will talk about partial symmetry in modular structures. Over to you, Berthold, please.
Yes, thank you very much, Vitali, and all the other organizers, obviously, of course. So maybe a few words about myself. So what I do is structure determination by single crystal diffraction. So I'm an experimentalist. I'm not a theoretician or something. So what we do is we take a tiny speck of a crystal, irradiate it with, I don't know, X-rays, electrons and neutrons, then record the interference pattern. From that, we can determine where the atoms are located, and then finally, we describe what we see. Yeah, so that's our job. I mean, it's a small contribution to science, but I think it's an important one. I mean, for one thing, we fill the CCDC and so on, and you can then do all these structure property relationships. And so the problem I have now is that usually I talk to other people who make the same thing, or to chemists who are interested in the results. So I'm not sure how well known all these things that we'll talk about are. So feel free to interrupt me if I use words that are completely strange. Yes. So wait a second. Yes. So the first slide is actually not related to the rest of my talk. It was just this mathematical crystallography.
Yeah. Shift, please.
Okay.
Just up. No, the bar.
Technical problems. Yeah. So I was just thinking, how does what I do relate to mathematics and to computer science, and was just brainstorming. And it turns out I was surprised how many different mathematical topics we're using for single crystal structure determination. There are too many to talk about them in one slide. So, but anyway, the point is that the whole thing is based on very different parts of mathematics. So we do I don't know, algebra, linear algebra, we do complex and real analysis, we have probabilities, and from computer science we also have optimization, we have complexity and all these things. So, but I'm not a mathematician, right? So I'm a chemist originally. I will not be able to tell you any new insights about these things, but I measured a few hundred crystal structures now, and what I can tell you is where I feel that the theory is still lacking, and maybe there are some mathematicians who have already solved it, but it's not yet gone to the crystallographic community, right? So, and one of these things where I think theory is lacking is this whole topic of partial symmetry, and this basically follows me since literally day one. So my first crystal structure I had to solve was calcium telluride, and it produced one of these diffraction patterns, like you see them here, very similar kind, which defy the classical categorization of is it crystalline or is it not crystalline? Because when it's crystalline, you would think it's periodic, and when it's periodic, it should have discrete diffraction pattern. Yeah. Now you have these diffraction patterns. We have sharp spots, discrete, and at the same time diffuse scattering. And sometimes you have diffusity to different degrees. And sometimes you have, like in the middle one here, you have spots that are not on a lattice. You would suspect they're on a lattice. And yeah, so that was my first crystal structure. And then I made more tellurides in my PhD. And they all had, not all, but many of them had these kind of diffraction patterns. They popped up more and more. So my conclusion was a bit that, well, it's tellurides that do this. So then in my postdoc, I expanded my field to phosphates and these kind of things and see there same things. And later I started to measure crystal structures for other groups, so organics, metal organics, intermetallics, all these kind of things. And also there, same kind of diffraction patterns. And so then I knew it was something very general. And this is a bit what I want to talk about the background, why this happens, but also a few examples so you get a feeling of what we're actually up to. And obviously, I'm not the first person who has noticed this, that often things are not are ordered but not ordered at the same time. Yeah, and there was especially one group in the 1950s and 60s around Dornberger Schiff, and they created. They thought about it. Why does this happen? And they created what's called the OD theory, where OD stands for order disorder. It's a bad name because it has nothing to do with order disorder phase transitions. And when you Google for order disorder, you find about these phase transitions. So I will just call it OD theory. And the idea is very simple. So you have a structure that is composed of layers, also rods, but I will not talk about rods today. And you have two kinds of those. You have non-polar ones, which are the same on both sides. They're symmetry relating both sides of the layer. And you have polar ones. So that's, oops. Yes, it goes away. And now the idea is the following. When you have these layers and they have a higher symmetry than the overall crystal structure. Like, for example, these two layers here, they have a reflection plane, which is marked by this line, by this segment. And the reflection plane of the lower layer is at a different position than the one of the upper layer. Now, when you apply the reflection of the lower layer to the pair of layers, then what happens? The lower layer is mapped onto itself, and the upper layer is mapped somewhere differently. That means you have generated a new pair, and the new pair has the same interatomic distances, obviously, because a reflection is isometry. But the second layer is located at a different position. And from the second layer, you can play the same game again. You have two ways, and then again and again. And then you get a structure where, like the one below, where go left, right, left, left, and anyway. But the crucial point to notice that if you look at pairs of layers, the pairs of layers are always the same. All the structures you can construct. Yeah? And so the thing is, this is what we call equivalence regions. And the largest equivalence region you can have in the family of structures, we call this maximal equivalence regions, or MERs. And really the crucial point is that these MERs, they cover your whole structure. So you have always this overlap here. It means place yourself anywhere inside such a polytype is different structures of the same layers stacked in different ways. Place yourself anywhere inside this polytype, and you have the same environment in all these polytypes, right? And that's what you call an order disorder structure. So the formal definitions, you have a finite number of types of layers, and adjacent layers share common two-dimensional lattice. And the important one is equivalent sides of equivalent layers connect to adjacent layers such that the resulting pairs are equivalent. So and what I want to propose is that, because the whole theory, it's always based on layers, but what I want to propose is that don't look at the layers, look at these MERs, how you can compose them, and such that the whole structure is covered by these MERs, because then in all the structures you are locally equivalent. And just aside, so this is a different way how you can construct these equivalent layers. That's when you have two layers that are related by an operation that turns upside down, like this glide reflection, but the resulting layer pair is polar, which means upside and downside are different. Then you can apply the inverse of this glide. So that maps the upper layer on the lower layer, and the lower layer somewhere different, right? And then you can, and the polarity, I have shown it here by arrows, so it goes either up or down. So one of the questions you could ask is, these equivalence regions or MERs, are they always pairs of layers? And no, they are not in some cases. And I show this with an example. It's a completely trivial compound. It's potassium hydroxide dihydrate. But crystal structure is a bit complex. So what you have is that you have a potassium atom surrounded by 8 water molecules, forming kind of a cube, a distorted cube. And the cubes are connected to these three-dimensional tetragonal networks. And in these networks, you have basically rods of empty space, and in this empty space are located the hydroxides. And now, if you look at the diffraction pattern, you know that you have these streaks along C star. That means with perfect order in the AB plane, but disorder in the C direction. And all these examples which I will show will always have the disorder in the z direction for rotation. So we know we have layers in the AB direction, and this is one symbolize such a layer. The squares are
the c direction.
So now in this, now we're looking down the z direction. So A is right, B is up, right? We're looking down the z direction. So that is one layer, and the squares are basically the cubes. And these hydroxides are represented by circles, basically. And what you see is that these hydroxides, they are moved in either to the right or to the left. And then the next layer is rotated by 90 degrees, and the next one again by 90 degrees. So here the hydroxides go in the other direction. And again, you can move them up or down. And the crucial point is that they have different lattices in these two layers. And then you apply OD theory, there's a whole bunch of theory. And that tells you then that you can combine these layers, but basically you can choose how these hydroxides are located. So either in one direction or the other direction. To get equivalent pairs. And then now you see this from the side. So now C is going up here, and we look here down B and here down A. And how the hydroxides are located, I represent this here by plus and minus, either this or that direction. And basically you can change it, right? Now, if you have a pair of layers, it's always the same. But even if you have a triple of layers, it's still the same. And in this case, it's even more extreme. If you take 4 layers and you distribute the plus and minus as you wish, it will always be the same. It will always be related by symmetry, and only starting with quintuples of layers will get differences. So in this case, our equivalence regions are 4 layers wide. And in all structures, 4 layers will always be equivalent. So that always means you are inside 4 of these equivalence regions. Now, the whole idea is that basically all the structures are locally equivalent. So basically, if you ignore interatomic interactions beyond 1 layer, then you would say they're energetically equivalent. So you would expect that all these structures are completely disordered. But you cannot do that. It's always a bit of a simplification, and there are ordered polytypes. Because simply, if you take one of the central layer and that has a reflection plane here, and you take the 2 other layers that violate this reflection plane, basically, then you will have some distortion inside this layer, and the reflection plane will not be perfectly realized. So what will happen is that triples will be slightly energetically different. So one may be better than the other, lower energy. So when you say that, for example, one of these triples is preferred, it's always the same, then you get one of these ordered polytypes. And if you say the other triple is preferred, you get this other polytype. And these are basically the simplest polytypes you can construct, and that's what you call maximum degree of order polytypes. The formal definition is MDO polytypes, you cannot decompose them into simpler polytypes, right? With less n tuples. So you would think if one of these triples is preferred, you will get these MDO polytypes. But there's also other ones, like this guy here to the right. This is right, right, left, left, right, right, left, left. This is non-MDO because you see you have triples from MDO1 and triples from MDO2. And in fact, this is the simplest of the non-MDO polytypes in this case. These do exist, they crystallize. It's not very logical, but it exists. And now for the potassium hydroxide example, there you have quadruples are always equivalent, but quintuples are different. And the difference is you look not at the plus minus in every second layer, but in basically every third layer. So you go 2 layers, and then you go left, left, that's one of the quintuples, or you go left, right, that's the other quintuple. And if you go in both directions, left, 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 you get this MDO polytype, it's monoclinic. And if you go right, left, in both directions, then you get this tetragonal polytype. And if we, for example, the simplest non-MDO polytype.
So what is the quintuple?
So
it's a rectangle. It's a
yes, right. One layer would be this here, and the second layer is this guy here.
Yeah.
And if you take 4 layers, they're always the same. And if you take from here to here, it's 5. They can be different. And they differ in
can
the
be
way,
shifted in another.
right? They differ in the way that plus goes left, or plus goes right left.
Yeah.
We ignore the second and third.
Yeah.
And so these are MDO, and in this case, actually, here we go in one direction, we go left, 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 left. But in the other one, we go right, left, right, left. That would be the simplest non-MDO polytype. And it turns out the actual structure is this, but not ordered. It's mostly this, but with some stacking force. That brings me to the next slide. What happens if we get stacking force? Because I mean, these triples are, we said, a bit different, but not much. So during crystallization, you would expect that it's errors. So if you look at this MDO1, we go left, 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 left. So macroscopic domain, and then we have a stacking fault. You go right, 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 right. That would be a twin. So we have two macroscopic domains with different orientation, and at the interface we have a triple of the other MDO polytype. But the more important thing is that these two twin domains, they share central layer. So usually when people think about twins, they think about you have one domain, then you have stop, and you have the other domain. But in OD twins, the crucial point is that you have an interface where basically you're in both domains at the same time. Now this other MDO polytype, this right, left, if you put in a stacking fault, you have an MDO1 triple. That's not a twin, that's an antiphase domain. You have two domains, but they are moved, but they have the same orientation, and we can't see them in diffraction. So these are always a bit difficult. But what we can also have is, for example, that we have one polytype, right, left, right, left, right, left, and then we start growing a different polytype. And you would think that's completely illogical, because why would one of these be preferred, and then suddenly during crystallization, the other one would be preferred? And the surprising thing is, these are, I would not say very common, but they are quite common. You see that really in some diffraction patterns, you see different ordered domains. But what can also happen is that basically the stacking fault probability gets high. Then what happens is that basically what we have is a disordered structure, right? And now you could ask the question, when is it a twin, when it's a disordered structure? Because, I mean, we have a stacking fault every 100,000 or every 1,000. The difference is basically phenomenologically. Is it bigger than the coherence length of our radiation, or is it smaller? Right? If it's bigger, then what we add is the diffraction pattern, which is the square of the amplitude. If it's smaller, then they diffract coherently. So what we see is basically interference between both, and then we add these complex values. Now, when we talk about these kind of structures, what really, let me start from a different angle. So symmetry is basically at the core of every crystal structure description, right? The symmetry is where I start, the space group symmetry. But when we talk about these OD things, and what this pointer made, it's always about, do we have local symmetry? And so we have to discuss partial symmetry for the structures. And now, so there's two things we often tell in our students. One thing is we say nature loves symmetry. And the other thing is we often say is there's no translation symmetry, because for translation symmetry, you need an object of infinite size. And obviously there's a contradiction. And I tried to show this with the centipede. So if we look at the total symmetry of this thing, it is finite, so it is point symmetry M, indicated here. You would say, okay, it's composed of 12 halves of different segments. But obviously this is not correct, because you could take one segment, translate it 2 to the right, and then translate it 4 to the right. And so clearly there is translation inside. If we look at the partial symmetry, that is, we do not map the whole space onto itself, but we take a subset of space and map it to another subset of space. And that's what chemists basically do when they say, okay, we have an SP of 6 on this and that position, and another one on this and that position. But what they do not do is, for example, they take 8 of these segments and move it 1 to the right. And then you see that the 7 inner segments are mapped onto themselves. And that shows that this centipede has actually quite a big symmetry, right? It's not low in symmetry, it's big when we just map parts of space. Now you could ask a question, what's the structure of this partial symmetry? And again, this is this example here. And I will look, usually what they did until now is look always at, you dissect space and look at basically not overlapping things, but what I want to do is look at overlapping things in our MERs or equivalence regions. And so let's take, for example, 1, 2, the pair 1, 2, and map it on the pair 2, 3. You have to flip it, so that's a C-glide reflection. And then you can take the pair 2, 3 and map it on the pair 3, 4. You have, again, flip it, and then you can, of course, combine it, and this gives a translation from 1, 2 to 3, 4, for example. So it's quite obvious that there's always the identity. You can, any object you can map onto itself without changing it. And it's also obvious that you have always the inverse. And I think it's also obvious that it's associative because it's composition of functions, which is a partial function, associative. So in principle, what we have is a group. And that's also the name given to this thing, groupoid, which literally means it's like a group. The only difference to a group is that you cannot combine any operation with any other. You can only combine an operation where when the target of the first is the source of the second, right? So like it's written here. And now these groupoids, mathematically, they're a special case of what is called a category. We'll have a talk on category by Greg McComb on Thursday, I think. And it's a very simple case of category. And the structure is not even that interesting, but it means that we can apply all these tools that the category theorists developed. One thing is these basically these diagrams where the nodes are your objects and the operations are the arrows, and then you can combine it and we say a diagram commutes when any path we take gives the same result. So C after C gives the translation. And so in itself, this the groupoid is not very interesting when the abstract groupoid, but when it gets interesting when you map it on space, when you say, okay, have a space like this and that. Now, but the really interesting question, crystallography, is always not one particular space group, but how can we relate space groups? That's basically the whole content of the tables A. And yeah, for space groups, it's clear you have an affine transformation that transforms the space group, which is conjugation here. And this gives the 230 or 219, depending on you allow inversion or not, space group types. Now for these locally equivalent structures, how does it work? Basically, what we can do is we associate every object on the left to an object on the right. And if they overlap on the left, they must overlap on the right. But now for each of these connections, we have an affine transformation, right? So from this to this and from this to this. So we have an infinity of affine transformations. And we have this, what we demand is that if we apply an affine transformation and then an operation on the right, it must be the same as if we apply an operation on the left and then the affine transformation. Right? And this you can show by this diagram here. So operation affine transformation, operation, and then we immediately, if we spell this out, we immediately see that we get something quite similar to this conjugation, but with different affine transformations. And that's what category theorists call a natural transformation. In this case, probably a natural isomorphism. Okay, so that's a bit the theoretical part, I think. Yeah. And so let's go to an example. I have 3 examples. I don't know if time will permit to go through all of them. So that's the crystal structure of this complex here. It's POCOP is basically this ligand, this chromium in the center and the bromine. And very, very strange crystallization behavior. Crystals looked completely different from the same crystallization dish. We isolated 2 polytypes, P bar 1, P to 1 upon C. And how do you explain that? And it's quite obvious if you look already at these two different polytypes. They have different stacking. So you see they have this layer in common. And again, here we look, C is now going down. And this is one of the layers. You identify the symmetry of these layers. It's not perfectly realized. You see it here, but it was PBMM. So the reflection plane in the layer, then the reflection went horizontally and the glide plane vertically. And now you want to determine from one layer, how can I go to the next layer, right? And you see it in the structure already. And from that, you can determine what you call the OD groupwood family symbol that tells you everything. That tells you what the symmetry of the layers are and how you come from one layer to the next. And that quite obviously is a coset down here because you have one operation, but you can apply operation from layer symmetry before that, so you get a coset. And if you want to determine how are the other possibilities, what you do is basically you look only at the operations that do not turn the layer upside down. And then you look at the operations. So the second layer is moved a little bit. You look at the operation that the layers have in common, and you do a coset decomposition. And you see in this case, you have from one layer to the next, you have 4 ways of placing this such that the pair is equivalent. You have down here these R and S, that's metric parameters that give you basically the shift that from one layer to the next. And in this case, that's not always the case. The layers are always translationally equivalent. And this is a very nice case for diffraction. I will go into this a little bit later. But the gist is you have 4 ways of translating the lower layer to the upper layer, indicated by these arrows here. And R and S are these metric parameters. And in our case, it's also a very nice case, as I will talk about later. It's about a fourth. So you go a fourth in this, a fourth A and a fourth B, either plus or minus. That's the 4 ways. Then we can think about what, again, we're looking down now. So C is going perpendicular to the drawing board. What are the polytypes with a maximum degree of order? They're also important because, as I said, all the other ones can be decomposed into these kind of polytypes. So pairs are equivalent. So we start with one pair, we go in one direction, but triples are different. So one way is we just keep going in the same direction, and that already defines a triple, and we get if we do that indefinitely, we get MDO1 polytype, it's triclinic. If we change the B direction, then again the triple is determined, and we always change the B direction, so we get a monoclinic polytype MDO2, or we can change the A direction, then we get MDO3, it goes right, left. Or we change both directions, then we go back and forth, basically, and that's another monoclinic polytype, which is MDO4. Interesting thing about MDO4 is, if you look at the lattice, that's an orthorhombic lattice. And people often get these orthorhombic lattices with monoclinic symmetry, and they think it's some weird coincidence. But in reality, it's often this thing. Yeah, there's an inherent symmetry to this thing, which gives you a perfectly orthorhombic lattice, when in reality it's monoclinic crystal structure. What you can also think about is what twins do you expect? So in this case, it's just from the pictures, obvious that you get 4 twin domains, because we can go in the 4 other directions. In this case, 2 twin domains. You can also do it formally by looking at the point group, and the point group, go back, the overall point group of this is MMM. The point group of this is bar 1, do a coset decomposition. And that's also important why you look at these MDO polytypes, because then you have the MDO polytypes, you know the lattice, and then the reciprocal lattice where you expect the reflections, it's always it's a reciprocal lattice. And so from the lattice of the MDO polytype, you can say where do you expect the reflections, right? And then in this case, here we have I only look at the H and K even planes, because that makes they're less complicated. You have rods where the family reflections are. These are reflections that belong to all polytypes. And these are always sharp. And then you have rods where you have different reflections. For example, the green ones belong to MDO1 and 3, but rotated, so the twin domain, and the red ones 1 and 3, another domain, and the blue ones 2 and 4. And on the other side, it's a bit different. So 4 never has a twin domain because it is an orthorhombic lattice, and it's just mapped onto itself. So it has twin domains, but you can see it in diffraction. And then you play a little bit this logic game for kids, where you have to find out who murdered who, getting hints, and you say, okay, you have reflection here, so it could be this guy, but you don't have reflection here, so it can be that guy. And then basically you can give a qualitative interpretation of your crystals. And I just pick out 3 crystals. We measured more, and then you can do the same thing with, in this case, with streaks. You can say, okay, if you have streaks on this and that rod, then it is a mix, a disordered mix of MDO2 and MDO1, for example. And if you have reflections which are more MDO2, you know it's more MDO2 with high stacking fault probability. And we get 3 different crystals here. Maybe let's start with, I don't know, with the crystal 3. It's only composed of ordered MD1 polytypes and 1 twin operation. That means in one direction, and I expressed this here with correlations. 1 means you never change direction, -1, you always change direction. You never, in the whole crystal, you never change direction in the A direction, but very seldomly you change direction in the B direction. So that's 1 minus epsilon if you want. And then with the second crystal, I go down up. So this guy here is pretty much the same thing as the third one, but the second twin domain, it has streaks, and the first twin domain doesn't have streaks. So you have 2 domains, one's perfectly ordered, and the second domain is a bit disordered. And the first crystal, it's completely different from the other ones. Basically, it's a mix of MDO2 and MDO1, more on the MDO2 side. So in the B direction, if we go back here, in the B direction, you change direction more often than not, but in the A direction, only very seldomly, which gives you this twinning. So that makes life a bit more difficult if you want to quantitatively evaluate the thing, because then you have to basically you have to simulate the diffuse scattering, but then you have to overlay the diffuse scattering of 2 twin domains, right? And then it could be that the actually parameters of these both twin domains are different. So it's quite difficult. And now I will change gear now quite completely, because I want to look at this crystal 1 here, because it has an interesting phenomenon, which is somewhere completely different, which is the phenomenon of homometry. It's long known, but it's I'm not sure how familiar but it stayed obscure, right? So the gist of it is 2 structures are homometric if they are different but have the same diffraction pattern. So you cannot differentiate from diffraction which of the 2 structures you have. So we say structures are equivalent if they are related by an isometry. And then there's this term by Bürger. He says 2 structures are tautoiconic if they have the same self-image, or the same Petersen function, or same pair distribution function. That basically means the weighted interatomic distances are the same, right? And homometric structures are the ones that are tautoiconic and not equivalent, because tautoiconic structures have the same diffraction pattern. There's a very informal argument that says what we measure is not the Fourier transform, but the square of the amplitude, and that you can write by simply multiplying it by its complex conjugate. And now if you take the inverse Fourier transform, what you get is basically the convolution of these 2 things. And the inverse Fourier transform of the Fourier transform is the scattering potential, so mu is the scattering potential. And the inverse Fourier transform of the complex conjugate is the scattering potential inverted at the origin and the complex conjugate. But we have basically real electron density. We have an imaginary component, but let's forget that. And you get the convolution of these 2. And that's the distribution function, basically. The argument is completely wrong. I have mathematicians here, because first of all, you cannot multiply 2 measures, especially if you have Dirac peaks inside. And this is also not given for disordered structures. So you have to be careful. We can save the argument for periodic structures, but also for non-periodic structures. And also this guy here obviously diverges. Yeah, you cannot take the convolution of two unbounded measures. So to make this more clear, here's an example of two homometric things. It's an unrealistic example. But basically, what you look in this pair correlation function is you look at interatomic distances and you plot them here. And these two things have the same interatomic distances, oriented interatomic distances, and with the same weighting. And that's why you get the same diffraction pattern. I try to make this.
I don't understand, sorry, because if you look at the upper example,
Yes.
there are these small distances.
Yes.
All three small distances.
Yeah, here.
Small.
Here's two small,
I see.
1, 2, 3.
They are homometric.
Yeah, they're homometric.
So you consider all pairwise distances together in one
Yeah.
huge distribution.
Yeah. So and also, as you know, the count has also to match. It's not only the distances themselves, but the count. And that show this here by these red arrows. You have these distances here and here, and you have 3. So this is weighted by 3, right? You have to have somewhat the same.
This is the diffraction pattern.
Right, it's the diffraction pattern, yes. And they give exactly. I've tested this. They give exactly the same diffraction pattern.
Computationally.
Yes. Yeah, this is just. For students, I have a small software where you can put in images and it gives a diffraction pattern, and you can play around with the image, and you see online while you play with the image how the diffraction pattern changes. That's quite fun. And I used this program and this. The times. I see.
For 10 minutes.
I lost a lot of time. I see.
We'll have a lunch break, so you go.
Yeah. Okay. So, but then we'll stop after this example. I have 2 others. Okay.
Fine.
No, this is not something you find in crystal structures, this kind of thing. So you might ask, does this really exist, this kind of thing? And yes, it does. And polytypes are one where this does exist, and especially simple cases when you have polytypes where all layers are translationally equivalent. Because then you can say the polytype is the convolution of one layer, and all the Dirac peaks at the origins of the polytypes. And then when you do this thing, this autocorrelation function, you will see that it's basically the autocorrelation of the layer and all these distances between the origins, right? And then you only have to have that these things here are homometric. And of course, yeah, this does diverge, so you have to look at some density. You cannot simply add an infinity of things. And in fact, for this example we had before, these are 2 homometric polytypes with a period of 12. They are, in ordered structures, they are exceedingly rare because, for example, for dense packing spheres, they start with 15 layers, with a period of 15. But it turns out that there are zinc, sulfide, and these kind of things. They exist. But with disordered polytypes, things change because they are even simple models give this homometry. And the problem is I've never seen really. It's all very hand wavy if you read that. I mean, there are examples, but it's super hand wavy just computationally, and there's not really a definition. So I tried to come up with a bit of a definition, and that's basically a little bit fast. So we have a layer, right? And then we have potential origin shifts from one layer to the next, and this is the point group of the layer. And in this case, I will just go to the right or to the left. So we ignore any shift in the b direction, and we have, in this case, 2 ways. And what's important is that this is basically closed under the point group of the layer. And then we can define a layer structure basically by infinite words over this alphabet or stacking possibilities. And yeah, and obviously one complication is that the origin shift is always modulo to the layer lattice, obviously. And that makes it difficult because if you have 1/4, if you go 4 to the right, basically you stay at the same place and this kind of thing. That makes it a bit more gnarly. And then we have finite fragments, and we can, for for reasonably well-behaved words, you can define a frequency of a finite fragment in that word. And then I would say that stacking sequences are the same if for all finite fragments, the density in the word is the same. Right? In reality, a bit more complicated, we would not look at fragments, but basically at the equivalence class with respect to the point group symmetry. So that left, 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 and right, 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 right is the same thing. But in any case, if we have a finite number of stacking thoughts, that is a stacking thought density of 0, that would be the same thing. But then we have to look at what happens if we add different origin shifts. And then, yeah, that's the thing that I said, then it gets a bit more complicated because, for example, we have a shift of 1/3. So in the second layer, we can go minus 1/3 or plus 1/3. Or minus 1/3 is plus 2/3, basically. And then from the second layer on, we have 0, 1, or 2/3. And if we have sixths, for example, in even layers, we can have even sixths, and in odd layers, we can have odd sixths. That's this clear, and we can then combine these to all possible origin shifts we have. And then when we have these origin shifts, basically in such a world, we can also compute derive the density of layers that are connected by these origin shifts. And that would be, you see, they are tautoiconic if these are the same, the densities of the layer shifts and the layers that are connected with layer shifts, and they are homometric if they are not equivalent but tautoiconic. But how do you describe these kind of things? So you describe them basically. Oh, that's how much time do I have? 5 minutes. How do you not describe? How do you model them? Because I mean that's what my job is. I have to have a measurement, and then I have to come up with a model, right? And in this ordered structure, what I find is, at least for my brain, the most logical thing is growth models, where I say, okay, you at least, I mean, it must not have grown like that, but in the description, you look at the S prior layers, that's the range of interactions, and from that you determine the probability of the next layer, right? So that would be range of interaction 1 model. You look at the last step, and we have a probability A that you make the same thing, and the probability 1 minus A, they'll make a different thing. And what I will require is that that's a Markov chain, the Markov chain that follows the symmetry of the layer. So left and right are just mirrored, so right after right must have the same probability than left after left. You know all these things, the transition matrix. And the range of interaction 2 model is here. So you have a probability LL after LL and LR after LL, but you can never have RR after LL because you look at the 2 priors. And the when you have these growth models, you can only give probabilistic statements. So you can express expected frequencies of the fragments of the origin shifts derived directly. But it's quite easy to see if they have the same transition matrix, then almost surely they produce almost equivalent stacking sequences. And if they are not, if we have not the same transition matrix, they will almost surely produce different stacking sequences. And now we say that 2 of these Markov chains are homometric if they're different, but basically what they produce is homometric. So, and just very quickly, if you have this range of interaction S1, it's not homometric, never will be, because simply we can compute, we go 2 up, what's the probability of that? And that must be the same in homometric structures. But that's 1 minus A. That means the A must be the same, not homometric. And the example I showed above, that was not of this case. That gives us these kind of chains give very special, what's the word I'm searching? Very characteristic peak shapes, which this didn't have. So we have to look at something like this. And now things are getting more interesting. Basically, in this case, you have A is 1 is MDO1 and A is 0 is MDO2. But when you have 2 neighbor interactions, we have LL after LL, that's MDO1 in principle, and B is LR after RL, that's MDO2 in principle. So we can now change this at the same time. And now what we have here is a two-dimensional parameter space. The blue one is the single neighbor model where I can go from MD1 to MD2. It's more or less sorted, but now we can also have these kinds of things here, where you say MD1 comes after MD1 and MD2 comes after MD2, and that would be an LO2, right? And we can say we switch every time. That would be the simplest non-MDO polytype. So in principle, the simplest non-MDO polytype has the same complexity as an allo twin. And that kind of explains, these are not very uncommon. These are also not very uncommon, but nobody wonders about these, but everybody wonders about these. And then just very shortly, if you go from, if this parameter is 1/4, so your step is plus or minus 1/4, then it turns out that these things start to be homometric, simply for very simple argument. So in every second layer, you have minus 1/4 or plus 1/4, but the Markov chain is symmetric, so this must have probability 1/2. So you can ignore them. So we have to only look at every second step, and we get a simpler Markov chain with parameters C and D. And when we back calculate, we see that we have lots of points, we have pairs that give the same diffraction pattern. Yeah, you see, I've connected these pairs by line, per line segment, to be more precise. And this is the single neighbor model. And you see, the closer to the single neighbor model, the less homometric you are. And on the single neighbor model, you're not homometric. And the most far you can get from this central line, the more different the structure, homometric structures, is precisely these. So the MDO1 and MDO2 allo twin, the left, left, right, right, left, left, right, right, give the same diffraction pattern under the condition that the coherence length of your light is larger than the domain state pattern. So I think I want to stop with that. Yeah, let's keep the conclusion slides. I hope that was somewhat interesting. Thank you.
Thank you, Berthold.
Okay, I'll stop the recording.